Maybe we don't.
No chalk?
No chalk at all.
Maybe later, actually, I am confused as to how to compute the atomic orbitals in the given
How to compute atomic
kinds
orbitals?
of atomic orbitals. Because we can compute the nearest
The second
neighbors from
problem.
here.
Okay, okay, good.
And
Good.
lattice.
I hope we can solve it. I just go and search it.
I think it is easy. I mean, since it's not it doesn't have a gamma prime, then
Which one?
it's a S only. This one. Because for
Yeah, this
B you
one.
have a gamma prime.
Like advanced technology, no? It's hard to find. Where was I? Yes. So we derived the Bloch velocity. You remember it was. And I would just like to spend time 2 to 3 minutes to discuss what happens in the case of the quasi-free electron in electric field. So normally, you know by heart now the dispersion. It's not greatly different for the tie binding, but this case it's a bit cleaner. So the energy, and we derived on Tuesday the velocity in K, but K is not in 1D. It's at 0. It's quite asymmetric to the result. 0, 0, 0. So I would just like to talk about how it happens that velocity changes sign. What occurs. So you have so asymmetric. We can write the wave function today as a Bloch state. Let's call it just G, X, and the G is the only vector, the magnitude of the vector of the reciprocal. This is obviously a Bloch state. No? You have a phase and a part which is periodic, but here is 2 pi over A, so it is clear. And then what happens when you start from 0? I think I gave names like A, B, C. At 0, you have a plane F. That's quite clear. Actually, you have it also in the tie binding. You have a cosine and very small k. It's 1 minus k squared. So very close to 0, they don't differ so much, tie binding and the typical tie binding band.
So
With the quasi-free electron.
it's clear that this wave function is okay with the Bloch
Yes, that's
theory,
clear.
but why do we write it in this form?
Okay, this is a very generic form. This is for any k under the influence of the field. I'll be just talking now. Maybe it becomes clear.
Okay.
So at the 0, you have only one form, only one part. Just that. Alpha and beta 0. And actually, it is not just the 0. For the quasi-free, it will be all the way to the inflection point at A, where it goes like completely like a free electron, parabolic. For tie binding, no. That's why I like this example better. So up to here, you have just this part. From A to B, what happens? Electron will start feeling the influence of the crystalline momentum Bragg plane. Did you do that? This is the whole reason why you get the opening of the gap. The influence of the edges are called Bragg planes. And that starts acting with the crystal momentum opposite to its direction. So, towards B, you are getting the beta larger. So beta is 0 here. As you move here, the beta starts growing up. It starts slowing down. This is A. A is the maximum, and then it starts slowing down, slowly. And what you're getting, well, first you will have a generic form. Well, I can just write the beta part. I think you can fill up in between, not to spend too much time. 1 plus beta Now I claim even that at the B point, at the very edge of the brilliant zone, the beta has to be 1. That might not be obvious at the moment. So K, let's say, is pi over A. And if I'm right that beta is equal to 1, let me just write it and then we see pi over A plus E minus. Correct? So this I should put on the side. Do you agree with this? So I'm saying here I impose that beta be 1. I haven't yet justified completely, but I just put it here. What do I obtain? What is this equation?
Cosine.
Yeah, okay, cosine. But it's a standing wave.
Yeah.
It's a standing wave. So at this point here, at the edge of the brilliant zone, your solution is a standing wave. Equal amount of going left and going right. So why could I use the beta equal 1? Let's see the C point. At the C point I have I know I have to have the same thing as this one, because it's the same point. And that I can obtain only if beta here is 1, and in this case I have minus pi plus alpha. Only if alpha is equal 1, and I obtain the same equation. So there is no other way to obtain it. They have to be standing wave at the both brilliant edges, brilliant zone edges. And as it goes from C to D, it's getting the opposite push than in this direction. Here it was moving in the opposite direction, it's pushing it in the opposite. So it just, the whole thing is just pushing it left and right if you look at it that way. Is it helpful? Is it, do you understand what I meant to say?
Yeah, I understand what you mean, but I don't get why the psi has been written as...
Yeah.
It's a generic way. With this, I can, in a quasi-free approximation, I can describe any state in the lattice. Here I have the influence of the field. So I'm looking how it moves through. This is a generic way. I know I have 3 electrons.
So you are writing in the block states are written as some phase times some periodic function.
Yes.
So what you are writing is you are expanding that periodic function.
In terms of these G vectors, which have an effect at the edges. This was just an example to see how velocity changes. Any questions? If not, we will continue with our current. In search of the missing current. So we finished Tuesday, at the point that even with the electric field, we didn't get the current. Because the average time average of a period was given 0. So then we said we have situation 2 ideal. We need to put some real life effects inside and scattering. What is scattering? I mean, it occurs because of impurities.
Yeah.
That's good. Impurities, and then there are many things.
Collisions with the atoms.
Yeah, also electrons.
Yeah.
And then there are also more advanced things. Electrons with the vibrations of the lattice, phonons. They all can cause this scattering, which is essentially impossible to remove. Even the best experimental growth techniques, they can remove impurities up to a good amount. The other ones, they're there. As soon as you have t different than 0, they're there. So we have scattering. Could get the picture. Anyway, so we have states, occupied states here, partially occupied band in equilibrium. Just the lowest states are occupied. What happens when you introduce the scattering? No, first the field, which would electric field. And they start moving. So this segment will go here, will go here, will come here, and go on. Okay, without the scattering. So the next step I can draw just to have the nodes. We will have these states occupied, and so on. It's moving under the field. And then we put the scattering. Scattering is usually to the states of lower energy. Otherwise it's not so. I mean, not only, but mostly. So you will have the states which are higher and which have available lower spots, lower energy states, scatter there. So in a way, the scattering will not allow it to move around, to sweep the brilliant zone. It will keep finding lower energy states to go there. And it's important to know that the scattering time is, I think, roughly 10 to the minus, I forgot, 14 or 16. Minus 14 seconds. Okay? While the period is much, much larger. This is scattering, and the Bloch oscillation. 10 to the minus 9, minus 10 seconds. So this is much shorter. So it won't have time to sweep the brilliant zone. It will scatter to lower states. So it will never go beyond some point, depending on this time, which depends on the origin of the scattering in the system. So you will end up with a situation which is not anymore the equilibrium situation. So this is under the field, and with the scattering. And here, and this is kind of frozen. This is happening all the time. And it will remain the situation. And now if you look at the current here, you will find it's not anymore. You don't have equal number of states with negative and with positive velocity. The current cannot be 0 anymore. It has to be a finite quantity. So this was finally a way to get the current. But very close to this is the question of how to measure the Bloch oscillations. I told you last time, it has been predicted, Bloch oscillations, almost soon after Bloch states, but they couldn't see them. They saw them I think like 10 years ago, 15 years ago, they saw them for the first time. So because you always have the scattering, I mean, you can reduce it 100 times, but not more. So it's impossible, it seems to be impossible to see to observe the Bloch oscillation of this segment traveling to the brilliant zone. So, do you have any idea how they actually observed it? The problem is that the scattering time is much shorter than the period, period of the oscillation. And this guy here cannot be reduced.
So we reduce the oscillation time experimentally, I guess.
How do you do it? You understood what he said? I want to make this one shorter. How?
Will the even stronger electric field work?
Oh no, because you don't want the field too strong. You're changing the properties of the system. Most of the things we are doing are in the limit of reasonably small fields. Large fields will cause nonlinear effects and change band structure, change many things.
Extremely pure lattices, low temperatures, optical lattices.
It will always use this. Okay, I mean, you're approaching the thing, no? Come closer.
But
What else?
but the oscillation is proportional to the distance.
Yeah.
Inversely proportional to A.
Yes.
And also inversely proportional to the absolute value of the electric field.
But the field we say we won't touch. I mean, in the most basic approach. But this is the key.
But,
This is the key.
but isn't it the one that we can control more
The field,
in the experiment?
but you are limited. You cannot increase it 1,000 times. I mean, the values of fields which are used are actually quite narrow. We talk about the 1,000-fold, 10,000-fold. So, okay, by careful growth, you can reduce the difference to 1,000 times, to 100 times, but still the field you cannot increase that much. But what you can do, you can increase the A, the lattice constant. Of course, you cannot make a lattice with 1,000 times like a pure element, aluminum or something, 1,000 times larger lattice. But you can construct a heterostructure, which is a layered structure. And each of the layers contains hundreds, I forgot the number, hundreds of layers. And this was made for the first time of a semiconductor lattice. Did I write down the material? No. However, this has hundreds and hundreds of layers, and the whole thing is around 1,000 times a lattice of a single material. And that's how you obtain overall. This is the A. This is the A. That's how you obtain much larger A, much smaller reciprocal vector, and also much smaller oscillation time. And they measured.
I have a question. If we are considering small electric fields, how practical is this? Because typically materials...
Not like small, experimentally used. What he wanted to obtain this effect with electric field, you had to increase it 1,000 times from the value that we use. It completely changes the material. If you had an insulator, it becomes a metal. I mean, it's completely, you cannot... Okay. But now let's see what happens. So this is okay. We understood that the current will be obtained in the case of the scattering and electric field. And we assume here a band which is not fully filled. What happens if you have a fully occupied band with the scattering, with the field. So I put the field and it's scattering. I allow for the scattering. What will happen with the current? The field will make it move. So there will be change in the dk over dt rate is constant. And the scattering, what will be the scattering doing? So
Will this scattering work at all?
that's the question. Will it work?
It looks like it won't, because these particles are fermions and one point in the lower energy is occupied and
And
most
you cannot take a second one.
Yeah.
So although you allow for scattering, there is no available states. There are no states to actually scatter to. And we won't have scattering. So we'll just have this uniform, distribution of states moving in the Brownian zone. But you will always have all states occupied. And having them all occupied, what will be the current?
Zero.
Zero. Is it a surprising result?
No.
You have a fully occupied band. You can assume it's a semiconductor or insulator. So, just as a reminder, what we did. So the current is equal to some sum or integral. What did I write? Integral. There is a factor here. I didn't write the factor. I think it's 4 pi over. I'm not sure. Electron. Okay. This current will get larger with electric field or smaller. As they keep increasing the field, the current will be increasing. So the current is proportional to the electric field. Okay. What about the scattering time?
It's constant because it depends on the material.
But let's say different materials. So let's say I can control input impurities into crystal. Up to a point I can be changing the scattering time. So let's say I'm increasing the scattering time. It becomes larger.
Sorry, what's the question again?
How will the current depend on the scattering time? Just intuitively.
Inverse.
Hey, larger scattering time, which means it will be able to get further before it scatters.
Yeah.
Larger means 10 minus 13. It's confusing, huh?
Yeah.
So, larger means it can go further, it can make it more out of equilibrium and make the stronger current.
Okay.
Do you see that? This is just like points to understand. This is all very, how to say, intuitive approach. We don't derive it, but just to understand the dependencies. We are not really deriving the real conductivity expressions, just to understand. Okay. Now let's use what we just derived. So, let's consider the current of a fully occupied band. I'm writing without all the factors of the volume integration and so on over the whole Brownian zone. It's hard to get the Fermi now. Over the whole brilliant zone, all the states. And I can actually call it, I can just break it into occupied and not occupied states. There is at least that I should write. And empty. This is my own way of calling them. I'm still taking into account the whole brilliant zone. Okay, but I know that the current of all the states occupied is 0. Here I just made an artificial distribution of, well, let's say, I call occupied all up to here, and these I call empty. But actually it's just the name. I'm still going over the whole brilliant zone, having the full band occupied. Just the name at the moment. Okay, if this is 0, which we just showed there, I can write the current of the this is the right way, sorry. Just to keep the signs right. Minus minus gives plus. So, if I'm able to break the integration range into 2 different parts of brilliant zone, I'm saying that the currents which are coming from the occupation of those parts have to satisfy this condition. They have to be opposite. Or I can say that the charge is actually opposite. So this is how we introduce the electron current. Today I have no voice, sorry. And the whole current. Which is quite handy if you look at it. This tells me that if I have a brilliant zone almost fully occupied, but just a few holes at the highest energy, I can express the current of the electrons by just doing the current of holes, which is 1 or 2 states, tiny amount of states, which might be easier to calculate. No? This gives me this possibility. And now I would spend a few minutes to talk about the semiconductors. I hope it's all a review for you, and I will add maybe something new that we haven't done. But in the case of nearly filled occupied band, so this is a typical case for semiconductors. Okay. Kx, the energy, and let's not write anything, it's known, it's in K. I'll call this the valence band, and this the conduction band, which means that the Fermi energy has to be somewhere in between. Where?
On top of the valence band.
Why?
It has to be on 0, I guess.
Okay, let's first say the temperature is 0. Let's assume there is no temperature effects, no Fermi Dirac yet. Where is the Fermi level?
Yeah, on top of the
The valence band? The top of the valence band?
Why?
Yeah.
It can be anywhere. in
Anywhere.
between, actually.
I don't have a way to define it. I can put it anywhere for T equals 0, for no temperature effects. But then what happens when I... Did you draw this thing? With Nadia? No. This is the Fermi-Dirac. The filling. And let's put a Fermi energy here. Let's just postulate. And the temperature is, how do I put, is larger than 0. This is the full filling. And then I go down. This is half. This is quite large temperature, I would say. What happens? At some point, here it's not full occupation anymore. Maybe I have to increase the temperature. It depends on the gap. Depends how big the gap is. Depends how large temperature I have to put to start really seeing the states here. Because there is this is a gap. So as I'm increasing the temperature, the states are going more and more to the conduction band. I'm creating holes here and creating state here. At this point, it is not random, it's not arbitrary where to put the Fermi level. It has to be put in such a way, such a place, that the equal number of states holes here and here. So this will completely determine my Fermi level. And it means if I have the same shape of the band, that the Fermi level will be exactly
0.
what is 0?
I mean, in the middle.
In the middle. That clear to everyone? Because you have to take equal number from here and put them here. You cannot lose electrons. But then I put a condition here. I said, if the bands are of the X shape.
Yeah.
Why did I say that? Now imagine a different case.
The shape kind of measures the distance depends on the shape. Then I have equal distance.
No, the gap remains. I just said the shape, not the gap. So let's say I have.
Because it has to be symmetric in the sense that the top band is fully occupied by holes.
Okay, not still the right argument, but maybe you're thinking, well, I don't know. Let's imagine a very drastic case that the conduction band is extremely narrow. And this one remains the same. What is the difference between this and this?
The width.
The width. But how many states, like let's say in this delta E, I have n states.
This has more states than this
Exactly.
one.
And in the same delta E, this chalk is hard to. I have much less states. So it means that I will actually have to go. I will have to go deeper to take the states, the same amount of states, like here, which means that my Fermi level will have to be shifted to lower. This is a drastic case. We normally assume that the Fermi level is around a half overall, but it is not exactly. I just want to point out it does depend on the number of states you have available. Yep, you all see that. Now let me. This is the Fermi-Dirac distribution. I can also approximate it with 2 times roughly, no? Here it's a good moment to talk about types of semiconductors. You know silicon? This is, like you mentioned, semiconductor, you think of silicon, the very first thing. I will come back to it also next lecture. Silicon has a gap of 1.1 eV, which is a small, no, real semiconductor. And what happens, let's see here, like if I take EC, the number of electrons in the conduction band, EC minus EF, I can write, okay, for the case of silicon, which is half gap, roughly. We use this approximation at the room temperature. Half gap is 0.5, and the room temperature is 0.025. Well, it's I'm doing the right numbers. Yeah, it will give something minus 22, I think. I really rounded up here. It was 1.55. No. So, what happens when I change? This is very small. But what happens when I change the temperature by 10%? This will go exponentially to 1.1, and this thing will change. You can have calculator. Will change drastically. They put the numbers here. No, I didn't put the numbers, of course. You can evaluate. This thing goes exponentially. So it is extremely sensitive to temperature, which is hard for applications. Can you be sure that the temperature won't change by 10%? You can have very hot days or overheating of the computers or something. You don't want your devices to go crazy in a hot day. But this indicates you can just evaluate. This is 10% increase in temperature. You get huge oscillations, huge variations of the number of carriers in the conduction band. This is a property of intrinsic semiconductors. Extreme sensitivity to temperature and dependence. But there is also a different type of semiconductors. Which you kind of engineer, which you can find them occurring, but typical case is engineering. So I used the example of silicon, I think, yes. Imagine that we can represent silicon as a simple square lattice, which is wrong, but just imagine. Silicon is 4-valent. It gives 4 electrons in the system. Everywhere. And then I inject in the system a certain number of material which has a different valence, similar properties altogether. It can be germanium, can be phosphorus, Which one I put as an example? I put phosphorus. So if you place, let's say they go substitutionally. Doesn't have to occur always, but let's say that they will replace one of the original atoms in the lattice. And the phosphorus is 5-valent. It means it will give 5 electrons in the system. But the system remains neutral. So you obtain that you have more conduction electrons, but the system remains neutral. Oh, great, I removed the picture, but you can still see. You will have more electrons here.
What do
At
you
the
mean
same
by
temperature.
neutral?
You add the neutral atoms. I don't add electrons as electrons.
Ah, yeah.
That can be done
Neutral by charge.
by charge.
Yes, okay.
By charging. Because it's a bit confusing. There are also different ways of doping with just electrons, but that's not what we are doing. You are doping with a full atom, which is neutral. But, what was I drawing before? It will create more occupied states. A little bit more, depends on how many of these impurities or these donors you put. So you obtain a current in the conduction band which is not dependent on temperature, which remains, which is always there. This is not dependent on temperature. This is extrinsic semiconductor. I hope I'm spelling it right. And this is used in most devices. This is not the pure thing. Do I have time? I think I could show an example of a diode. Just to get an idea. But not just for the sake of diode, but to get a bit more familiar with the levels and the feeling and the fields and just a very, very simple am I missing something? By the way, this doping is extremely small. You do it in the perturbation theory. You still keep the silicon lattice, and this is like 1 in a million something. So you can still take it as in the perturbation theory. Your crystal remains periodic, your bands are the same, just a small perturbation. Okay, so the diode can be seen as the N or P doped, as an interface of the N and P doped semiconductor. Here we doped with electrons. This is the N doped case. That's very hard. N doped means you have a conduction band, you have a valence band and the conduction band. N doped, everything is filled here, and I have some states occupied in the conduction band. Not many, because it's then you change according to there is an interface, and you have a P doped system. This is valence, this is the conduction. This means it has holes. It would say that not all the states with respect to the previous situation are filled. No, I'm a bit exaggerated. It is a small amount. Let's say equal amounts of doping of N and P. And you put them in contact. So this is the initial case of the N doped and the P doped. Let me write it doped, don't get confused. You put them in contact. What happens?
So the ends move to the...
Yes. These are higher energy, and here they are holes. Naturally, after putting them in contact, these guys will shift there. Nice note, no? And then you are creating, let me draw electrostatic potential. You create actually a potential between the two of them. And upon doing that, you are depleting these regional electrons. They are going, moving, and here also they interact with holes. So you create a part, okay, my own chart, which is depleted. So let me try to draw it now. N and P, that the conduction band of the N is very close to the valence band of the P dot. This is and here is the conduction. And there is a depletion region. But it cannot go forever. It has to stop. It cannot take all the electrons from, because also there are limited numbers. So at some moment, it stops. They create this kind of arrangement. And you end up with a depleted part and almost align the conduction level of the N dot and the valence level of the P dot. Good. At this moment, to get a diode, you know what diode is. Okay. You would apply a voltage over this device. The first voltage will be the negative one to lift this guy up. So what you will get? This was all occupied, and here there were just a few states. Huh? Now you're getting all filled here and nothing here. You make a negative voltage, which lifts the EC of this one above the E valence of this one. What happens? You have only a few states which can go to a completely filled band. How would the current be? Now, or very, very small. Because this guy is, there is just the number of these impurities that you had holes, but even that is actually depleted. So the current is very, very small in this case.
I really don't quite understand how did we get this middle.
When you put in contact two systems with a different Fermi energy they will try to thermalize.
Yeah.
They will try to put the Fermi level at the same energy.
Yeah.
So when you contact them, they will do whatever it takes. They will shift electrons. They even can turn the bands a bit at the interface to obtain this condition.
But why did we get this shift of?
Because as long as there is a difference between them, there is a potential for these guys to go down.
Yes.
So you're filling these, you keep pushing them up, you're emptying these.
So the Fermi level of the N part goes down.
Yes.
Okay.
Yes.
But it's not necessarily true that the EC and the EV of the N and P are always will be the same level.
Depends on the doping. This is, a rough condition, yes. Okay, so for the case of negative bias, it's called bias, but whatever. the current is now. In the other case of positive, I don't have any space, there is this, of the positive bias, you can already see that things will be very different. So positive bias, closer. No, actually it's the opposite. Now what we have, condition that the completely filled band is higher in energy than the band which is mostly empty. And you can see, the more you increase the bias, the more you stimulate these electrons to go down. And the current is proportional to the voltage in this case. So you will get a typical, they call it IV characteristic of a diode. But for negative voltage, current is zero. And then, as you increase the voltage, it's linear. In other words, the current can go only in one direction. And this was the basis of the technology. Not sure how many years ago, to say 50 years ago or something. Okay, a small illustration of how these levels and what you know now can be practically applied. Okay, continue with this one.
But if on the right case,
Yes.
so the middle painting is for zero voltage.
Yes. Just by having them in contact.
Yeah. If we apply negative voltage,
Yes.
the left part, the end part, is just lifted up.
Yes.
But if we apply even stronger,
Yes.
then
I was saying that this
if this EV is
but
above,
this is again, this is full.
no, if the left EV is higher than the right E conduction,
Oh,
it will still.
that's a big voltage.
It's possible.
I guess it's possible, yes. But I'm talking about the useful feature now. I haven't thought you go that much higher. Because these things are all very sensitive. With applying high voltages, high fields, things are changing inside. You actually can close the gap altogether. It's not a constant with voltage, just for small range of linear behavior, linear response, it can be done. The same question.
So if the material has a bigger band gap, you can increase the electric field.
But it's not in your interest. Yes, it would mean that. But you don't want, you like semiconductor because the gap is small. It's easy to. Otherwise, if it's something big, you have to apply huge fields, and it's going out of the regime sometimes. I mean, there can be 10 eV gap. It's huge. Okay, now we go back to the band structure and the scattering, and very intuitively we can write the scattering force. So, how did I call it? Oh my God. this is always on the floor. This is what we derived on Tuesday. This is the force. If you remember, we are doing dk over dt, and we found that this has to be the force. Okay, I have a force in a system with electric field. So this force has to take into account this. That's obvious. But now I'm introducing completely intuitively, without a real physical, derivation, something I'll call the scattering force. There is an inclination to scatter. There must be something of that type. So I will see where this takes me. It will come back to the semiconductors. But I have a force, and from Newton's law, I know there must be some acceleration involved. Force equals mass times acceleration. So let me try to derive that acceleration. And I think I was doing it for a component, only one component. Yes. So let's see for the alpha component. So this is alpha. It's x, y, or z component. How I can find the time derivative and the acceleration in that direction. So this is just a component of the acceleration. So let me see. I will do what I know how to do. Decay. I can write this. Maybe it's not obvious right away why I'm doing it, but this is the part I want. Because I want to come to this expression. Okay. This is okay. This is just a weird way of putting it, but I think you see it's okay. And then I can write the velocity, the alpha component, as the 1 over h alpha of the energy. Energy is in total. This is beta. Let me write separately. K beta d over d k alpha of this energy. And I still have dk beta dt. And I forgot the 1 over h, no? To write this, I need 1 over h. This one. Okay? I'm just writing what we know. It's maybe not the most obvious where I'm going to, but what did I just write? That dvk alpha dt is equal to 1 over h sum over beta I want an h here to get the same thing as there. So I'll write an h, which means I have to take an h, put it in the denominator. This is what we obtained. This is the acceleration component in the alpha direction. Here we have something that looks like a scalar product. Something of the beta and something of the beta here. This is the force. This is the beta component of the force. You agree? This is acceleration. So we have acceleration is equal something times the force. If you take all the components, this is just alpha component here. And what this thing has to correspond to dimensionally?
Mass. Inverse of mass.
Inverse of the mass. But you see, it's a tensor. we managed to complicate our life to introduce the mass tensor, even inverse mass. This is, the way to write the tensor, the inverse of the tensor. So we are actually able to connect the acceleration of an electron in a band to the derivative of the current, but this time second derivative, which is not so surprising in a way. Velocity is the first derivative, this is the second. Somehow intuitively it's not completely off. So this mu, how did I? And one component, just one component of this mass tensor is equal to not any sum. And 1 over h squared. So to be able to estimate the acceleration, we have to find the second derivative of energy and then take an inverse. What if you have a free electron band? What is the... by the way, this is something called effective mass. This is the mass that electron moves in electric field, the influence of the force, as if he had this mass, or hole. The same can be for the holes. And these guys can be thousands times larger than the electron mass, can be positive and negative. We will come to that. So, for a free electron case,
it would be the same for any component alpha and beta.
Yes, it will be the same.
And positive.
And will be equal to the electron mass.
Yeah.
Okay, so I'm sorry, I use various notation. One is mu. I also use m star for the free electron case. You can derive it is h squared k squared over 2m. You can take the second derivative, you get 2 h squared over m over 2m. h squared cancel. You get inverse mass is equal to 1 over m, which means that it's equal for the electron mass. That's the simplest case. To solve these problems, you sometimes need to do inverse matrices. Can you do them?
Yes, but do we like doing it? No.
No, but even I give you like 3D, and if it's not just diagonal, it's a real pain. Now, I don't think it will do anything difficult. It might be something diagonal or like that, or not many times. Don't worry, don't spend your time solving inverses of the matrices. So, what happens? Again, semiconductor. Here we have the valence band minus assuming the free electron. Here is the conduction plus okay, sorry. 2. This is roughly the shape. Roughly. What will you have? We take a second derivative here. You will get a mass, this one. Well, I can write it right away. mass. This is the hole. Well, this is an electron, yeah. You will get a positive effective mass. Here, you take a second derivative. You will get a negative. So, they notify. They call it hole or well. M effective is minus M, if you assume this is electron mass. So it depends on the dispersion. Is it concave or convex, the band? This will give you the answer if the mass is positive or negative. If it's steeper than the electron mass, then the mass is, I always have to think of that actually. If it's steeper, in comparison to the free electron case, let me draw it in the positive. So this is free electron case. This is another one.
Smaller.
It will be smaller than the electron mass. You see, it depends on the shape. So you can read so much just from the band structure. And this depends on the direction, on the point in the Boolean zone and in which direction you go. At the same point, going in X or in W direction, whatever, will give you different values. And okay, I removed that expression where I wrote the force. Scattering. And now I can say it is actually equal to the, let me just see, yeah, here, to the effective mass so this is correct, no? We can and if we have a free electron-like system, we can express this V as F1 over H, K, or energy, to be equal, free electron will give you this. Okay, this is something I will put in my part I wrote just based on dimensional analysis and intuition. So I will have minus, so HK is equal VK times effective mass is equal effective mass times acceleration. But if I take a system, a stationary system, which doesn't move, no acceleration, I can obtain this condition. I can find that effective mass times the velocity is equal to minus, no? No, sorry, I was missing this scattering time. Now I'm saying I don't have one element. I'm writing with this big chalk. I don't know. Okay, it's a bit messy. So I can express the velocity as minus E scattering and the effective mass. So for the holes, for the electrons, let's put electrons first, and for the holes. By the way, does this look familiar? I can put this E out.
Ohm's law.
It's something that Drude derived. You remember? Let me see if I did obtain the right. Yeah, there is no density. Depends if it's current density or absolute current. The difference with respect to Drude, the effective mass, essentially. In the case of electrons, the minus scattering over the positive. Just in this case, no, I'm considering this case. This is not a general thing. I'm just looking at a semiconductor which has parabolic dispersion around the band, the conduction maximum, a minimum, and valence maximum. But for the holes, we'll get minus E, because it has to be positive charge, which means I have to also add minus in the mass, which is true. It has a negative. So this is a positive charge. There is a bit of confusion in the definition of currents of holes in electrons. You can find different books coming to different signs or the same sign. We derive this way, so let's keep this sign. Is there anything else I wanted to say here? I gave some, before I had some examples of the different effective masses, but that you can find in any book. I think Kittel has a nice table, and depending, you can get like thousands of times electron mass. Any questions? No? Okay. I hope it means it was so clear. Okay, now we still have a few minutes. We can solve a problem. Actually, I mentioned the problem with this alpha kx squared plus ky squared because it's actually an effective mass problem.
Okay.
That's why I wanted you to look at it. And this is just an application. I mean, it is still a pre-electron problem, but it's an illustration of. So maybe stop copying and you finish. We can try to solve. Did anyone solve it? Or try to solve? You did, Jesus? No, you did something like this, so I thought it was yes. Anyway, the problem which was giving the energy dispersion as kx squared. I think there was a constant before. No one. And then I won't be solving it on the blackboard. You should try to solve it. There is no point of me giving the solution then. No, I thought maybe one of you couldn't find time, but no one. You tried. No, it's okay. If you try and spend time thinking, it's what I want. I mean, if you solve, great. But this is a bit tricky. You have to realize one thing. And if you don't realize it, you won't move forward. But if you're the only one who tried, I don't want to solve it. You haven't.
Maybe we can solve it on the blackboard.
Yeah, but if nobody tried. I'm asking if you tried, not even if you solved. You tried?
Yes, but I don't want to come to the blackboard.
Oh, come on, anyone can come. It's a very simple mathematics. I will help with the trick part. I mean, it's not a trick part, it's just you have to realize something. And that's it. You tried? No. Kinda. You read it twice and thought of it. No, I know there is no time. It's just that the course is finishing relatively soon, so it's better if you... How many try? Let me see. 1, 2, 3, 4,
Like
5.
this, I'll raise my hand like this.
5.5. Okay, anyone volunteering to come to the blackboard to try to solve it? It's a very simple mathematics. It's not
Maybe
a mathematical. Okay, come on.
Can we stop the video?